Welcome to solverfy.
In this problem, we're looking at the 1s state of the hydrogen atom, which is the ground state orbital. And the problem wants us to show whether the wave function for this obeys the Schrodinger equation, which amounts to asking if the function is reasonably well behaved for the differential equation defined by the Schrodinger equation. So that amounts to asking questions like if it's continuous and single valued and finite over the range of integration, which in this case is radius 0 to infinity. Um, it also has to be square integrable, so psi squared has to equal a finite number when integrated from radius 0 to infinity. So for the most part, it's really psi squared that matters. But the in this case, psi squared has the same basic functional form as psi. So the only difference is that there'll be a factor of 2 that comes into the exponential, and the constant is slightly different. So the shape of those curves is the same, roughly. They're just slightly offset. So it looks something like that. So we can ask some questions. Is it continuous over the range? And it manifestly is. There's no kinks or breaks. Is it single valued? And in this case, it's the psi squared one that really matters, because that's what's the observable part, and multi-valued would mean that there's multiple probabilities at the same distance, which is unphysical. So that amounts to a vertical line test. So at no point is there multiple values of the wave function for a given parameter distance r. Is it finite? From radius 0 to infinity? And the answer to that is yes, because if this is 0, then it's e to the 0, and psi no, actually, I miswrote that. There's supposed to be a square root here. So that's finite. And at infinity, the whole thing goes to 0. And that's for the wave function, but I'll actually do an integral for the psi squared case to prove it. So just to be extra careful, for the continuity of the psi squared, um, well, okay, it doesn't just have to be continuous. The first and second derivatives have to be continuous, because those are terms in the Schrodinger equation. So those also have to be continuous. I wrote that as a partial derivative of habit, but this is a one-dimensional case, so strictly don't need to do that. So the first derivative of the wave function uh, so because it's an exponential function, the term up in the exponent stays the same under derivatives, and it just pulls the constant out, which in this case is minus 1 over a naught. So I probably should have put the negative sign with the 1 over a naught, but that's where it came from. So the second derivative of 1 over SR, or I mean psi 1s, pulled out another negative sign, so those cancel and brought out another 1 over a naught, so that becomes 1 over a naught squared. So that is the same functional form that we have up here. So all the arguments we just made are valid for the first and second derivatives also. So you should also do that for the psi squared, just for completeness' sake. So, so that is 1 over pi a naught cubed. So that becomes minus 2. Actually, I'm just going to be slightly more careful. Uh, I'm just splitting the constants apart that way and make it clear which terms are coming from the derivative and which are not changing. It's going to be convenient to write that way in a second. So again, it's the same functional form as the above cases for the psi squared. So it is continuous, and all of those same arguments we made before apply to this situation. It's finite and everything like that. So this wave function definitely does obey the Schrodinger equation. The question also wants to know what the energy is for the 1s orbital state, and that's kind of ambiguously worded. So this is the Schrodinger equation. This is the energy term. So I assume what it wants is energy as a function of radius. Uh, it doesn't specifically ask for it at the Bohr radius, but I'm going to find that anyway because that might be what it ultimately wants. So uh, we calculated these just a second ago. So um, these aren't the square and the squared. These are just the wave function, these side terms. So that was the pi over a naught cubed versions. So this is the second derivative one. So that one was positive. So that's minus h bar squared over 2me multiplied into that whole expression there. And then that is I'm going to write that down here. So I'm just continuing minus ke squared divided by r c, and energy is also multiplied by that exact same factor. So the way I've written this makes this particularly easy to see. So the wave function term here, this is just the what we had initially. Um, these constants all you divide by both sides. So that was the right hand side. That goes away. That goes away. That goes away. Um, these because the exponential term doesn't change under differentiation. That didn't change, so that's the same on both sides. So right hand side, left, that goes away. That goes away. That goes away. So the whole thing is going to end up being let's use bar squared 2me plus 2 over r. So this is the radial dependence on energy. Now that might be all the question is really asking for, because it doesn't say anything more specifically than that. But it might, I suspect it wants to know about the case where the radius happens to be the Bohr radius, um, which is just the most probable position. It doesn't have to be at that. It could be any. The electron cloud means the electron could be anywhere in the range. It just has different probabilities. So in this particular case, you just substitute in the values. So that ends up being uh, so that is positive h bar squared over 2 me is ke squared. So I put all the constants here. This whole thing is a constant. So energy in this case ends up equaling minus 2.18 times 10 to the minus 18th joules. But electron volts are slightly more convenient. So if you were to convert that into electron volts, you would find that the 1s orbital state for the hydrogen atom from that wave function is minus 13.606 electron volts, which is the ground state energy value for the Bohr model. So there's an exact correspondence between the two, even though the Bohr model is not in general correct, but it is right for this case.